Confidentiality, secrets stay secret. Opening the database that faced the wrong way. There is a particular kind of silence that happens in a security team's Slack channel right after someone types the words, "I think our customer database is public." It is not panic, not yet. It is the silence of everyone simultaneously doing math. How many records? How long has it been like this? Has anyone outside the company already found it? What does public even mean in this context, and who can answer that fastest? That silence is the entire reason confidentiality exists as a concept worth studying rather than a single-line item you tick off once. Confidentiality is the promise that information will be seen only by the people who are supposed to see it. It sounds almost embarrassingly simple when you say it out loud. And yet it is the property that fails most often, fails most visibly, and fails in ways that cannot be undone. You cannot unleak a database. Once the information is out, every subsequent action is damage control, not prevention. So this session is about that promise. Where it comes from, what holds it up, what happens when it cracks, and what it actually looks like when an organization keeps that promise under real pressure rather than just writing it down in a policy document. The foundation, what confidentiality actually protects. Let's start with a framework that everyone in this field eventually has to recite, because it is genuinely the right starting point, even if it gets treated as a box to check. Confidentiality, integrity, and availability. The CIA triad describes 3 different properties that information can have, and confidentiality is the first of the 3 for a reason. It is usually the first thing people think of when they hear the word security, and it is often the property that, when it fails, causes the most reputational and regulatory damage. Confidentiality is the property that ensures information is accessible only to those authorized to see it. That's the textbook definition, and it's correct, but notice what it does not say. It does not say information is hidden from everyone. It does not say information is locked away and unusable. It says information is accessible to the right people and inaccessible to everyone else. Confidentiality is fundamentally about drawing a boundary, not about building a vault with no door. Integrity, by contrast, is about whether the information is accurate and unaltered. If someone changes a number in a financial record, that's an integrity failure, even if no unauthorized person ever read the record. And availability is about whether the right people can get to the information when they need it. A system that is so locked down that even authorized users can't reach their own data in a crisis has an availability failure, even if confidentiality is perfectly intact. Here is where it gets interesting, and where the textbook definitions start to develop tension with each other. Consider a hospital's electronic health record system. A patient is wheeled into the emergency room unconscious, no ID, no way to ask them about allergies or medication history. The attending physician needs that patient's record right now. Every second spent authenticating, every additional approval step, every, "Are you sure you have permission to view this record?" prompt is a second where a decision is being made with incomplete information. In that moment, availability is winning the argument against confidentiality, and it should. Most well-designed health record systems have a break-glass mechanism, a way for a clinician to override normal access controls in an emergency, with the explicit trade-off that doing so generates an audit trail and triggers a review. The system is not abandoning confidentiality. It is acknowledging that an absolute confidentiality posture, one that never yields, even in a true emergency, would itself become a danger. The record stays confidential from the general public, from other patients, from anyone without a legitimate clinical reason. But within the boundary of people who might need this to save a life right now, the access control loosens, and that loosening is itself a documented, intentional, logged decision. Now take the opposite extreme. A defense contractor stores the technical specifications for a weapons system. Here, confidentiality is not just the priority, it is close to the only priority that matters in the short term. If an engineer has to wait an extra hour, go through a supervisor approval, and use a hardware token before they can view the document, that is not a bug in the system. That is the system working exactly as intended. Nobody is dying because access was slow. Someone might die eventually, somewhere, if access was fast and wrong. These two examples are not contradictions. They are the same triad, the same three properties, weighted completely differently because the consequences of failure are completely different. This is the first thing to internalize about confidentiality. It is never evaluated in isolation. It is always evaluated against integrity and availability for this specific system, for this specific kind of information, for this specific moment. A security architect who treats maximize confidentiality as a universal goal, applied identically everywhere, will eventually either kill someone with a slow emergency room system or leave a vulnerability in a weapons database because they spent their hardening budget on the wrong system. The tension, locking the door without losing the key. If there is one tension that defines confidentiality as a practice, it's this. Every mechanism that keeps information away from the wrong people also makes it harder to get to the right people. There is no such thing as a control that only blocks bad actors. Every lock can be locked against the person who's supposed to have the key, too. If the key is lost, if the system glitches, if the policy is written too rigidly, if the person managing access leaves the company without documenting anything. This tension shows up at every layer. Encrypt a hard drive, and you've protected the data if the laptop is stolen. But you've also created a single point of failure around the recovery key. Lose that key, and the data is just as inaccessible to its rightful owner as it would be to a thief. Implement role-based access control so that only the finance team can see payroll data. But now when someone moves from finance to engineering, if the access isn't revoked promptly, you've created a standing risk that didn't exist when access was more ad hoc, and arguably worse, but at least visible. The deepest version of this tension is the one between confidentiality and usability, sometimes called psychological acceptability. A security control that is so cumbersome that people root around it doesn't protect confidentiality. It just changes where the leak happens. If your DLP system blocks every attempt to send a spreadsheet outside the company, including the ones a salesperson legitimately needs to send to a client, the salesperson doesn't stop sending spreadsheets. They start using their personal email, or a USB drive, or a messaging app that isn't monitored at all. The confidentiality boundary you drew on paper and the actual confidentiality boundary that exists in practice can diverge wildly. And they diverge in exactly the direction you didn't want, toward less visibility, not more. So the central tension of this session is this. Confidentiality is enforced by drawing boundaries around information, but every boundary creates friction, and friction that exceeds what people are willing to tolerate doesn't strengthen the boundary. It pushes the information across it through an unmonitored path. Keeping secrets secret is not just about building walls. It's about building walls that the people inside are willing to live with. Because the moment they're not, they'll find a door you didn't build and didn't know about. The architecture of keeping secrets, confidentiality by layer. If you wanted to draw confidentiality as a system rather than a single control, you draw it in layers, because that's how it actually gets implemented, not as one big lock, but as a series of smaller locks, each covering the gaps the others leave. The first layer is data at rest. This is information sitting on a disk, in a database, in a backup tape, in a cloud storage bucket, not moving, just existing. The primary control here is encryption, typically something like AES 256, applied either at the full disk level or at the level of individual database columns or files. The idea is simple. If someone gets physical or logical access to the storage medium itself, they steal the laptop, they get unauthorized access to the storage array, they find an old backup tape in a box. The data on it is unreadable without the decryption key. The data sits there present, but meaningless without the key. The second layer is data in transit. This is information moving between 2 points, a user's browser and a web server, one microservice talking to another, a database replicating to a backup site. The primary control here is transport encryption, most commonly TLS, with TLS 1.3 being the current standard. The threat model is different from data at rest. Here, the concern is someone intercepting the communication as it travels, a man-in-the-middle attack, someone sniffing traffic on a shared network, a compromised router silently copying packets. TLS wraps the conversation in an encrypted tunnel so that even if someone captures every packet, what they capture is ciphertext. The third layer is data in use, the trickiest of the three because at some point, for the data to be useful, something has to be able to read it in plain text. A database query has to decrypt a column to compare it against a search term. An application has to load a customer's address into memory to print a shipping label. This is the layer where access controls do most of the work, because encryption alone can't protect data that's actively being processed. You need to control who and what is allowed to ask for that processing to happen in the first place. This is where access control models become central, and it's worth being precise about the differences between them, because interviewers love this question and the differences actually matter operationally. In a mandatory access control model, or MAC, access decisions are made centrally based on classification labels. Think of a government system where a document is labeled secret, and a user has a clearance level, and the system enforces that a user without secret clearance simply cannot see the document, full stop, regardless of what any individual administrator might want. The owner of the resource doesn't get a say. In a discretionary access control model, or DAC, the owner of a resource controls who can access it. If you create a file on your computer, you decide who else gets to read or write it, which is flexible but means security depends on every individual user making good decisions, which, across a large organization, is a fragile assumption. Role-based access control, or RBAC, sits in between in a practical sense. Access is granted based on a user's role within the organization, so everyone in the finance role can access the payroll system. And when someone's role changes, their access changes with it, in theory. RBAC is the model most enterprises actually run on because it scales. You manage roles, not thousands of individual permission grants, but it carries its own failure mode, which we'll come back to. Roles accumulate. People move between roles and keep the old access, just in case. And 18 months later, an audit finds that a third of your users have permissions that map to no current job function at all. The fourth layer, often underappreciated, is data in motion between organizations. What happens when information has to leave your direct control entirely, headed to a third party? This is where data loss prevention systems live, watching outbound email, file transfers, cloud uploads, and flagging or blocking content that matches patterns for sensitive data. A string of digits that looks like a credit card number, a document tagged confidential, a file containing what looks like a database of names and social security numbers. DLP is the layer that exists because, no matter how good your encryption and access controls are, eventually an authorized person is going to take some authorized data and try to send it somewhere. And sometimes that somewhere is a mistake, the wrong recipient in an autocomplete dropdown, a personal email account instead of a work one, a public file sharing link instead of an internal one. And underneath all of these layers sits a fifth, foundational one: secrets management. Not secrets in the sense of the company's confidential documents, but secrets in the sense of the credentials that everything else depends on: API keys, database passwords, encryption keys themselves, certificates. If the key that encrypts your data at rest is sitting in a plaintext configuration file in the same repository as the application code, your encryption at rest control is, for practical purposes, decorative. Tools like HashiCorp Vault exist precisely to be the place where these foundational secrets live, not in code, not in config files, not in someone's password manager that they forgot to revoke access to when they left, but in a system designed specifically to store, rotate, and audit access to the keys that everything else relies on. Notice the shape of this architecture. It's not one wall. It's a series of walls, each one assuming the others might fail, each one covering a different way information can move or be accessed. Confidentiality as an architecture is the assumption that no single control is sufficient, layered with the assumption that every control has a blind spot that the next layer needs to cover. The tools examined honestly. Let's go through the core tools that enforce confidentiality, but let's do it the way a practitioner would. Not just what each one does, but what it costs, and more importantly, what it doesn't do, because that's the part that gets people in trouble. Start with AES 256 disk encryption. What it provides is exactly what it sounds like. If a device is lost or stolen while powered off, or if a drive is physically removed from a server, the data on it is unreadable without the key. This is enormously valuable. Lost laptops are one of the most common ways organizations lose control of sensitive data. And full disk encryption turns: we lost a laptop with customer data on it, from a breach notification event into, often, a non-event. What it costs is mostly in key management overhead. Every encrypted device needs a recovery key stored somewhere safe. And somewhere safe needs to be more available than never, because a forgotten password on an encrypted drive with no recovery key is just as much data loss as theft would have been, just self-inflicted. What it does not do is protect data once the system is powered on and unlocked. A stolen laptop that's already logged in, or a server that's been compromised while running, has its disk encryption working exactly as intended and providing zero protection, because the decryption is happening transparently for the attacker too. Disk encryption protects against the threat of someone has the physical disk. It does nothing against the threat of someone has access to the running system. Next, TLS 1.3 for data in transit. What it provides is protection against interception. Anyone capturing network traffic between two TLS-protected endpoints sees encrypted noise, not the actual content. TLS 1.3 specifically also provides better forward secrecy than older versions, meaning that even if a private key is compromised later, past sessions encrypted under that key generally can't be retroactively decrypted. What it costs is mostly in certificate lifecycle management. TLS depends on a chain of trust rooted in certificates, and certificates expire, and an expired certificate doesn't just create a confidentiality gap. It often takes down the service entirely because browsers and clients refuse to connect. What TLS does not do is protect data once it arrives at either endpoint. If your web server receives a request over a perfectly configured TLS connection and then logs the entire request body, including a password field, into a plaintext log file, TLS did its job flawlessly, and the data is still sitting there in plaintext on disk. TLS protects the pipe. It says nothing about what happens to the water once it arrives. Next, data loss prevention. What it provides is a safety net for the moment when authorized data is about to leave through an unauthorized or risky channel, catching the accidental email to the wrong address, the upload to a personal cloud account, the USB copy of a customer database. What it costs is, candidly, a lot of tuning effort and a real risk of becoming an obstacle people root around. DLP rules built on pattern matching, looking for things that resemble credit card numbers or social security numbers, generate false positives constantly, because lots of numbers look like other numbers, and a sales contract that happens to contain a string of 16 digits for an unrelated reason gets blocked just as readily as an actual leaked card number. What DLP does not do is stop someone who is determined and even moderately sophisticated. Someone who wants to exfiltrate data and knows DLP exists can take a screenshot, can rename a file extension, can encrypt the file themselves before uploading it. Now it doesn't match any pattern, or can simply read sensitive information off a screen and retype it elsewhere. DLP is excellent at catching accidents and unsophisticated insiders. It is not a control against a motivated, informed adversary. Next, vaults, secrets management systems like HashiCorp Vault. What they provide is a single, audited, access-controlled location for the credentials and keys that applications need, replacing the anti-pattern of credentials embedded in code, configuration files, or environment variables scattered across dozens of systems. What they cost is architectural complexity. Every application now needs to authenticate to the vault itself before it can retrieve the credentials it needs for everything else, which means the vault's own access control becomes extremely high value and high consequence, and the vault itself becomes a single point of failure if it's unavailable. Your applications can't start. What a vault does not do is fix bad habits automatically. A vault with a static, never-rotated root token that's been pasted into a dozen Slack messages over the years is not meaningfully more secure than a config file. It's just a config file with extra steps. The value of a vault comes specifically from dynamic, short-lived credentials and tight access policies, and an organization that adopts the tool without adopting the discipline gets very little of the actual benefit. Finally, role-based access control itself, as a tool rather than a concept, implemented concretely as, say, Active Directory groups mapped to permissions. What it provides is scalability. You manage a manageable number of roles instead of an unmanageable number of individual grants, and when someone joins, you add them to a role and they inherit everything that role implies. What it costs is the ongoing discipline of keeping roles accurate, which is a process cost more than a technology cost. RBAC doesn't fail because the technology breaks. It fails because nobody updates the mapping when the organization changes. And what RBAC does not do by itself is prevent privilege accumulation. RBAC tells you that a user has the permissions of their assigned roles. It says nothing about whether those roles still reflect what that person actually needs. And over time, in almost every organization that doesn't actively fight it, the answer drifts toward no. Implementation, two decisions that sound simple and aren't. Let's walk through two implementation scenarios the way you'd actually have to think through them, with the pushback included, not smoothed over. The first is full disk encryption rollout across a fleet of corporate laptops. On the surface, this is almost a checkbox. Enable BitLocker or File Vault or LUKS depending on the operating system, and you're done. The actual decisions start immediately after that. The first real decision is recovery key management. Where do the recovery keys live? If you're in a Windows environment integrated with Active Directory, BitLocker recovery keys can be escrowed automatically to Active Directory or to Azure AD, which means it can retrieve a key if a user forgets their password and gets locked out. But that escrow location is now extremely sensitive. Anyone with access to read those recovery keys, effectively has a master key to every encrypted laptop in the organization. So the access control on the recovery key store has to be tighter than the access control on almost anything else in the environment. And it needs its own audit trail, because who looked up this person's recovery key and why is exactly the kind of question that comes up during an insider threat investigation. The second real decision is what happens at the help desk. A user calls in, locked out, needs their recovery key. How does the help desk verify this is actually the laptop's owner calling and not someone who's stolen the laptop and is now socially engineering their way to the decryption key? If the answer is they read back the employee ID number, that's a weak verification, because employee ID numbers aren't exactly secret. This is where the implementation of a purely technical control, disk encryption, runs straight into a process control. Identity verification procedures for the help desk, which is a people problem wearing a technology hat. The third real decision, and the one that gets skipped most often, is what happens to the recovery key when an employee leaves. If the recovery key was generated once at enrollment and never rotated, and an employee who left 6 months ago happened to write it down somewhere, or had access to the escrow system as part of their old job, that key is still valid. Disk encryption that's never rekeyed after a relevant personnel change is providing a static guarantee against a population of people who might have once known the key that only grows over time and never shrinks. None of this means full disk encryption is a bad idea. It's close to mandatory for any organization handling sensitive data on portable devices. It means that implement full disk encryption is not a single task. It's a technical control plus a recovery process plus an identity verification process plus a key lifecycle process. And an organization that implements only the first of those four has implemented something that looks complete in an audit checkbox and is actually only about a quarter complete in practice. The second scenario is configuring a web server for TLS 1.3. Again, something that sounds purely technical and quickly becomes organizational. The technical steps are well understood. Generate a private key and a certificate signing request. Get the CSR signed by a certificate authority. Install the resulting certificate and configure the server to prefer TLS 1.3 and disable older, weaker protocol versions, and select a cipher suite that supports forward secrecy. The first non-obvious consideration is the certificate's chain of trust. A certificate signed by an intermediate CA needs that intermediate certificate installed alongside it, or some clients, particularly older mobile devices or certain corporate environments with their own trust stores, will see untrusted certificate errors even though the certificate itself is perfectly valid. This is one of the most common sources of "the site works for me, but not for some users" tickets, and diagnosing it requires understanding that trust isn't just about the certificate, it's about the chain. The second non-obvious consideration is renewal automation. Certificates expire typically every 90 days for free automated certificates, up to a year or more for commercial ones, and an expired certificate doesn't degrade gracefully. It doesn't make the site a little less secure. It makes the site inaccessible, with browsers actively blocking the connection and showing security warnings to users. This means that from a confidentiality standpoint, certificate expiry is technically an availability failure, but it's caused entirely by a confidentiality and integrity mechanism, the certificate, which proves both who you're talking to and gives you the key material to encrypt the conversation, failing closed. The fix is automation, tools that handle certificate renewal without human intervention. But the implementation question is what happens when the automation itself fails. If the automated renewal process breaks silently 3 months before a manual process would have caught it, You've traded a known, scheduled task for an unmonitored dependency. And unmonitored dependencies are exactly the kind of thing that fail at the worst possible time. The third consideration is what happens with internal traffic. It's easy to focus TLS effort on the public-facing website and forget that traffic between internal services, the web server talking to the application server talking to the database, is also data in transit, and is also subject to interception if an attacker gets a foothold inside the network. Mutual TLS, where both sides of a connection present certificates and verify each other, extends the confidentiality boundary inward, but it multiplies the certificate management problem by however many internal services you have, which is exactly why organizations running containerized environments often adopt a service mesh, specifically to handle this certificate issuance and rotation automatically. Because doing it by hand for dozens or hundreds of internal services isn't sustainable. In both of these implementation scenarios, the pattern is the same. The headline technical control is the easy part. The hard part is the life cycle around it. Who has the keys? What happens when something expires or someone leaves? How failures are detected before they become incidents, and how the process scales as the organization grows. Confidentiality implementations don't fail at rollout. They fail 18 months later, quietly, when nobody's watching the thing that was supposed to keep working on its own. When confidentiality breaks, 3 failures worked through. Theory is one thing. Recognizing what a confidentiality failure actually looks like while it's happening, and more importantly, how to trace it back to its root cause, is a different skill. Let's work through 3. The first scenario. An internal certificate suddenly shows as untrusted for all users, but the certificate itself is not expired. Someone reports it Monday morning. Everyone internally is getting a browser warning when they access an internal application, and the help desk is starting to get flooded. The first thing to check is exactly what the error says, because untrusted can mean several very different things, and they have different causes. If the error specifically mentions the certificate has expired, that's straightforward and we're in a different scenario, but we've been told it's not expired, so we move on. The next thing to check is whether this is happening for all users or a subset. If it's a subset, the pattern of who's affected is the clue. Is it everyone on a particular operating system, or everyone who joined the company in the last few months, or everyone using a particular VPN connection? Suppose the pattern turns out to be everyone on company laptops is fine, but anyone using a personal device or a contractor laptop is seeing the error. That pattern points directly at the trust store. The internal certificate was likely issued by an internal certificate authority, and company-managed laptops have that internal CA's root certificate installed via group policy, so they trust certificates signed by it. Personal and contractor devices never had that root certificate pushed to them, so from their perspective, the certificate is signed by an authority they've never heard of, which is, correctly, untrusted. But wait, the report said this started suddenly on Monday morning for devices that were presumably working fine before. If the root cause were simply personal devices never had the CA root installed, this would have been a problem from day one for those devices, not something that started suddenly. So there's a second layer here. Something changed. The most likely culprit is a certificate renewal. The internal CA itself issued a new intermediate certificate as part of a routine rotation, and the web server was updated to present the new certificate chain. But the new intermediate certificate either wasn't included in the chain that's served to clients, or was signed by a slightly different path than the old one. Company-managed devices, which trust the root CA directly, can validate the new certificate even with an incomplete chain, because their systems may already have the relevant intermediate cached, or because their trust path doesn't require it explicitly. But anything relying on the server to present the full chain, which is the correct, standards-compliant behavior, breaks. And that breakage happens not to be masked for devices that trust the root directly via a separate mechanism. The fix is to ensure the web server is configured to present the complete certificate chain, including the new intermediate, and then to verify this using a tool that checks from the perspective of a client with no special trust configured, exactly mimicking the personal device's view, rather than testing only from company laptops, which is why this could have gone unnoticed during testing if testing was only done from managed devices. The deeper lesson is about testing assumptions. It works when I test it is only meaningful if your test environment matches the environment of the people reporting the problem. And trust store configuration is exactly the kind of environmental difference that's invisible until it isn't. The second scenario. A data discovery scan finds hundreds of files containing personally identifiable information sitting in a web server's public upload directory. This is, in confidentiality terms, about as bad as it gets short of an active breach. The data isn't behind any control at all. It's just sitting there, reachable by anyone who knows or guesses the URL. The first thing to do before any investigation into how this happened is containment. Remove public access to that directory, or move the files out of it entirely immediately. Every minute these files remain reachable is a minute where someone could be downloading them, and the investigation into how did this happen doesn't need the files to stay exposed while it runs. With containment done, the investigation starts with a simple question. How did these files get into a public upload directory in the first place? Public upload directory suggests this might be a directory designed to receive files uploaded through some web form, a job application portal accepting resumes, a customer support form accepting screenshots, something of that nature. If that's the case, the next question is who put PII-containing files there. Did a user upload a file that happened to contain PII? Someone attaching their own ID document to a support ticket, for instance. And the application simply stored it where it was put, with no classification or access control applied to uploaded content. Or is this an application misconfiguration, where files that were meant to go into a private storage location were instead, due to a configuration error, written to a directory that's served publicly by the web server? These two root causes lead to very different fixes. If it's the first case, users are legitimately uploading documents that happen to contain PII, and the application has no concept of this uploaded content might be sensitive. The fix is architectural. Uploaded files need to go to storage that is private by default, with access mediated through the application itself, so the application can verify that the person requesting a file is authorized to see it, rather than being directly served by the web server from a public path. If it's the second case, a misconfiguration, the fix might be narrower, correcting the specific configuration error, but it should be accompanied by a broader question. How many other directories on this server have the same misconfiguration, and how would we have caught this sooner? The answer to that second question is usually some form of continuous scanning, specifically for this pattern. Publicly accessible directories containing files that match PII patterns, rather than relying on someone stumbling across it. The third scenario. A DLP policy fails to block the transfer of a file labeled confidential to a personal email address. The label exists, the policy exists, the transfer happened anyway, where's the gap? The investigation here has to separate three things that often get conflated: the label, the policy, and the enforcement point. The label is metadata attached to the file. Something has to have applied a confidential classification to this specific file. The policy is the rule that says files labeled confidential should not be sent to external email addresses. The enforcement point is the system that's actually positioned to see the email being sent and check it against the policy. Start with the label. Was this file actually labeled confidential at the time it was sent in a way the DLP system can read? If the classification was applied through a document management system as metadata, but the file was downloaded from that system, and the download process stripped the metadata, which happens more often than people expect, because metadata doesn't always survive a save as or a format conversion. Then by the time the file is attached to an email, it's just a file with no label at all, and a policy that triggers on confidential label has nothing to trigger on. The DLP system isn't failing to enforce the policy. It's correctly enforcing a policy against a file that, from its perspective, isn't classified. If the label did survive, the next question is whether the policy itself covers this transport. DLP policies are often configured per channel: email, web upload, USB, cloud sync. And it's entirely possible for a policy to be thoroughly configured for, say, the corporate email client, while a separate webmail access path, a user logging into their personal Gmail through a browser, and attaching the file there, isn't covered by the same policy, either because it's a different enforcement point entirely or because that specific channel was never enabled when the policy was rolled out. If the label survived and the channel is covered, the last place to look is the policy logic itself, and specifically whether the policy is in a mode that actually blocks or a mode that only logs and alerts. It's common, especially early in a DLP rollout, to deploy policies in monitor or audit mode first, specifically to avoid the false positive disruption we discussed earlier, with the intention of moving to block mode once the policy has been tuned. If that transition from audit to block never happened because tuning takes time, because nobody wanted to be the one to flip the switch and potentially block something important, then the policy has been faithfully logging every violation, including this one, for months. And the policy didn't work is more accurately. The policy worked exactly as configured, and it was configured to only watch. What this scenario reveals, across all three possible root causes, is that confidentiality controls have dependencies on each other that aren't always visible. A DLP policy depends on a classification system working correctly upstream of it. A classification system depends on metadata surviving every transformation a file goes through. And a policy depends on someone having made the deliberate, sometimes uncomfortable decision to actually enforce it, not just observe it. The view from different seats: how confidentiality looks depending on where you sit. The same principle, secrets stay secret, means something different depending on which role is thinking about it, because each role encounters confidentiality at a different point in its life cycle. The security architect encounters confidentiality at design time, and their central question is always, where does this data live, and what's the smallest set of paths it can travel through to get from where it's created to where it's used? When a new application is being designed, say, a system that will process patient health records, the architect isn't asking, should this data be encrypted? Of course it should. That's almost not a decision at this point, it's a baseline. The architect is asking harder questions. Does this data need to be in this database at all, or can it be tokenized, with the actual sensitive values stored in a separate, more tightly controlled vault, and replaced everywhere else with a reference token? Does the reporting team that wants to build dashboards on this data actually need the raw patient identifiers, or can they work with a de-identified version? Every place this data is allowed to exist is a place that now needs encryption at rest, access controls, audit logging, and a breach response plan. So the architect's job is as much about minimizing the number of places the data needs to exist as it is about protecting each individual place. This is the data minimization principle, and it's a confidentiality control that works by reducing the attack surface rather than hardening it. The data that was never copied to the reporting database can't leak from the reporting database. The compliance and audit professional encounters confidentiality retrospectively, asking, "Can we prove this was protected the way we said it was?" This is a fundamentally different activity from designing the protection. An auditor doesn't usually get to watch the encryption happen in real time. They get to ask for evidence. Show me the configuration that proves disk encryption is enabled on this fleet of laptops. Show me the access logs that prove only authorized roles queried this database in the last quarter. Show me the policy document that defines what confidential means and who's allowed to apply that label. The auditor's relationship to confidentiality is evidentiary. A control that exists but produces no log, no configuration record, no audit trail, is, from the auditor's perspective, and increasingly from a regulatory perspective, indistinguishable from a control that doesn't exist at all. This is also where the question of trade secrets, copyrights, patents, and similar intellectual property protections connects to confidentiality directly. A trade secret's legal protection depends entirely on the owner having taken reasonable measures to keep it secret. If a company's most valuable formula or algorithm is sitting in a shared drive with no access controls, and it leaks, the company may find that a court doesn't even consider it to have been a protected trade secret in the first place, because the legal definition of a trade secret requires that confidentiality was actually maintained, not just claimed. Confidentiality, in this sense, isn't just a security property. For certain categories of information, it's the thing that makes the information legally yours. The security automation engineer encounters confidentiality at the level of the pipeline. Specifically, the moment where a piece of automation needs a credential to do its job, and that credential has to come from somewhere. Every automated process, a script that pulls data from an API, a deployment pipeline that pushes code to production, a monitoring tool that queries a database, needs to authenticate as something, and that something has a secret attached to it. An API key, a password, a certificate. The automation engineer's relationship to confidentiality is operational and constant. Every new pipeline is a new place a secret might need to live, and the default, the path of least resistance, is almost always to put that secret directly into the pipeline's configuration, often in plain text, often committed to the same code repository as everything else, because that's the fastest way to make the pipeline work today. The discipline required here is resisting that default every single time, routing every credential through a secrets management system instead, even when it's slower, even when it's the third time this week, because the alternative, a credential sitting in a Git repository, doesn't fail loudly. It just sits there, working fine, until someone makes that repository public, or until an old commit is found by someone scanning GitHub for exactly this pattern, which people do constantly, automatically at scale. The automation engineer's confidentiality failures are almost never dramatic in the moment. They're quiet, accumulated, and discovered much later by someone else. What ties these three perspectives together is timing. The architect is asking, how do we prevent this before the system exists? The automation engineer is asking, did I just create a small leak in the middle of building something dozens of times a week? And the auditor is asking, can we prove it didn't leak after the fact, sometimes years after the fact? Confidentiality, as a property, has to survive being looked at from all three of these temporal positions simultaneously. Designed correctly, operated correctly day to day, and documented well enough to withstand scrutiny later. Capstone scenario, the database that faced the wrong way. Let's bring this together with a scenario, and let's give it real constraints, the kind that don't have a clean engineering solution, only a managed trade-off. You're the on-call security engineer for a healthcare technology company. It's a Tuesday afternoon. Your company runs a cloud-hosted database containing patient records, names, dates of birth, medical history summaries, insurance details, for a platform used by several mid-sized clinics. The database lives in a cloud provider's managed database service, and like most managed cloud resources, it has a network access configuration that determines what IP ranges or what scope can even attempt to connect to it. A junior developer has been working on a new feature, and to test it from home, outside the corporate VPN on a Tuesday afternoon trying to hit a deadline, they changed the database's network access setting from restricted to the corporate VPN range to open to all IP addresses 00000. It's a one-line change in a configuration panel. They make it, their local development environment connects successfully, they keep working. They do not think of this as a security event. They think of it as removing an obstacle. Here's the constraint. This is a managed cloud database, the kind of thing where a configuration change like this takes effect within seconds, and where the database, the moment that change is live, is technically reachable by anyone on the internet who has the host name and valid credentials. And depending on how authentication is configured, valid credentials might be a username and password that, while not trivial to guess, is also not protected by the network-level barrier that was, until 30 seconds ago, doing a significant amount of the actual security work. The database didn't get less encrypted. Its access controls at the database level didn't change. But one of the layers, the network layer, the one that says, you can't even start a conversation with this database unless you're coming from somewhere we trust, just turned off. The first part of this story, in an organization that hasn't built anything to handle this, is that nothing happens for a while. The developer finishes their feature. The change either gets reverted manually at some point, or, just as plausibly, gets forgotten, because it worked, and there was a deadline and nobody flagged it. In the organization we're describing in this scenario, something different happens, because the organization has implemented exactly the kind of automated guardrail this mental model is named for. A continuous configuration monitoring system, something like a cloud security posture management tool or a custom policy check, is continuously evaluating every database resource in the cloud account against a baseline. Databases containing data tagged as falling under healthcare privacy regulations must not have network access configurations broader than the corporate VPN range. Full stop. No exceptions. Because the data classification itself, this is patient data, places it in the category where this particular control is non-negotiable. Within roughly a minute of the developer's change taking effect, the monitoring system detects that this specific database's network access configuration no longer matches its required baseline. The system has been configured for this specific class of violation, overly broad network access to a database tagged with regulated health data, to take an automated remediation action rather than purely alerting. It reverts the network access configuration back to the VPN-restricted range, and it sends an alert to the security on-call channel describing exactly what changed, on which resource, and that it has been automatically reverted. You, as the on-call security engineer, see this alert. The database's exposure window was on the order of a minute, not a Tuesday afternoon. Nobody outside the organization had time to discover this. And even being thorough about it, you pull the database's access logs for that window and confirm that the only connections during that period came from the developer's own IP address, the one they were testing from, which the automated revert has, incidentally, also now blocked, meaning the developer's connection drops and they come looking for someone to ask why. Now here's where the trade-offs get real, because the story doesn't end with the automation worked, hooray. The developer is now blocked. They had a legitimate reason to want to connect from outside the VPN range. They were working from home. The VPN was, let's say, having intermittent issues that day, and the broad network access change, however poorly chosen, was solving a real problem they were having. The automated guardrail has correctly prevented a confidentiality exposure, and has also correctly prevented the developer from doing their job for the rest of the afternoon, and they now need an alternative. This is the constraint that can't be engineered away. The same network restriction that protects this database from the entire internet also restricts the small number of legitimate engineers who sometimes need to reach it from outside the office. You can't simply fix this by making the restriction more permissive. That's the exact failure mode the guardrail exists to prevent. And you can't simply tell the developer, too bad, use the VPN, because VPN reliability issues are a real operational problem that, left unaddressed, will produce more of these one line, just open it up for now changes by this developer or others, the next time they're under deadline pressure and the VPN is being difficult. So the actual fix, the one that's defensible, not just technically functional, has two parts. The immediate part is reverting the developer's change, which the automation already did, and confirming no exposure occurred, which you've already done. The structural part is addressing why the developer felt they needed this change in the first place. If VPN reliability is a recurring problem, that's a separate ticket, with its own owner, and it needs to be treated as contributing to confidentiality risk, even though it's a networking and infrastructure issue on its face. Because every time the VPN is unreliable, you're incentivizing exactly the workaround that just happened. And there's a third part, the part that's easy to skip when the automation worked so cleanly that it feels like the story is already over. This incident, however small, however quickly resolved, gets documented. Not as a punishment for the developer. The goal here is not to make people afraid to make configuration changes, because fear produces silence, and silence is worse than mistakes you can see. It gets documented because the pattern, engineers sometimes change network access settings to solve immediate problems, without realizing the data classification implications, is exactly the kind of pattern that, if it shows up once, will show up again, possibly on a database where the automated guardrail hasn't been configured yet, because the organization has dozens of databases, and the guardrail was rolled out to the highest-risk ones first. The documentation from this incident becomes the evidence. The next time someone asks, do we actually need to extend this guardrail to the rest of our databases? For why the answer is yes, not hypothetically, but because it already happened once here on this database on a Tuesday, and the only reason it didn't matter is that the guardrail happened to already be in place on this particular system. The result then isn't just the patient data stayed confidential, although it did. The result is a small piece of evidence about how the organization actually behaves under realistic pressure, deadlines, flaky VPNs, a developer trying to do the right thing the fast way, and a slightly better informed decision about where the next guardrail goes. That's what it looks like when confidentiality is treated as a property of the system as a whole, including the people and the pressures they're under, rather than a property of any single control considered in isolation. Closing, the discipline of drawing boundaries. If you remember one thing from this session, let it be this: confidentiality is not a wall. It's a boundary, and boundaries have two sides, and your job is never just to make one side impenetrable. It's to make sure the right people can still cross from the other side reliably without wanting to dig a tunnel instead. Every encryption key you manage is a boundary that depends on someone being able to retrieve it when they legitimately need to, and on no one else being able to retrieve it ever. Every access control list is a boundary that depends on staying current as people's roles change, which means it depends on a process, not just a configuration. Every DLP rule is a boundary that depends on being strict enough to matter and loose enough that people don't simply walk around it. Every certificate is a boundary that depends on a chain of trust that someone, somewhere, has to keep renewed correctly forever or it fails. And when it fails, it doesn't fail quietly toward less security. It fails loudly toward no service at all. The practitioners who are genuinely good at confidentiality are not the ones who can name the most controls. They're the ones who, when they hear about a new system being built, immediately ask where the data is going to live, how many places it's going to be copied to, who's going to need to touch it and how often, and what happens on the day someone needs access in a hurry and the normal process is too slow. They think about the boundary from both sides every time, because a boundary that only works from one side isn't a boundary. It's just a wall with the door already kicked in, waiting for someone to notice. Secrets stay secret, not because they're locked away and forgotten, but because someone, deliberately and continuously, is managing exactly who gets to open the door, and watching to make sure the door doesn't quietly come off its hinges while no one's looking. End of session, mental model. Confidentiality, secrets stay secret.